Hello, this is the third, final part of lecture 3 of linear algebra, and this part is about system of linear equations and elementary row operations. So basically, the main goal of this lecture is to apply the tools we already studied about matrices to solutions of linear equations. Okay, what are system of linear equations? System of linear equations is a system of equations that looks like this. This is probably the simplest possible equations we can imagine. So here x1, x2, xn are unknowns, and a11, a12, amn are some real numbers, and b1, b2, bm are also some real numbers. Okay, we already met such systems of equations earlier in this lecture in the first part, and in the lecture 1 in illustrations. Okay, so once you see such system of linear equations, you can ask 3 important questions. Are there solutions? If we have solution, then how many? And if we know how many, how to compute them? So basically all these 3 questions will be addressed in this part of this lecture. Okay. So basically, we're going to use some results about matrices, which we already studied and learned, and we're going to use these results to answer the first 2 questions theoretically. And then we study something which some of you already know, which is called elementary row operations, basically to show how to compute solutions for system of linear equations. Okay, so note that the system above, this system, can be rewritten in a matrix form like this. Yeah, so basically we already did this several times, and this is the most important link between matrices and system of linear equations. Okay, by the way, small remark that system of linear equations appear everywhere. So basically in every problem that involves mathematics in real life, at some point you're going to see a system of maybe complicated, maybe huge system of linear equations. And in general, it's not easy to solve this system without help of computer, but even with help of computer, you need to know some tools and some methods how to solve the system. Okay, good. So let us consider one very explicit example with 3 unknowns. Yeah, suppose you have this system of linear equations. So first advice from me is, if you see such not very complicated system of linear equations, if at some point you're uncertain about which tools to use, remember that you can solve this system accurately without no tools, just by basically simplifying this. The main idea is how to simplify the system of equations until you get something very simple, such that it's easy to solve. Okay, what can we do? So first, we notice that the second equation is quite simple, so we can probably have to put it first. Yeah, so we swap first equation and the second one. Yeah, so we have this. Okay, then we can use the first equation, yeah, to simplify the third and the fourth. Look, if I have this system of equations, if I subtract first equation from the second, but multiplied by 2, I basically kill this term x. X disappear, and you get something like this. Similarly, if I take the first equation, multiply it by 3 and subtract from the third equation, I get this. So why do I need this? Because it's clearly that this system of equations look a little bit simpler than original one. Yeah, we don't have x here, we don't have x here. So you can keep doing this. So for example, now you can get rid of y. Yeah, you can multiply this equation by 7, add to the last one, and you kill y term. There's no y term here. Yeah. Now, when you look at this equation and you see, okay, basically we don't need to solve it. It's already solved. Yeah. Third equation gives us z. We substitute this z into the second equation. We immediately obtain y. And then we substitute z into the first equation and we obtain x. So we found unique solution. Okay. So this is absolutely straightforward. And the only delicate issue that when you simplify your equation step by step, you must remember that you should be able always go back. So if I did some simplification to this system, I get to this, you should be able to return back. You should be able to play with these equations to obtain original ones. So if you do it in consistent way, it's good, it's guaranteed that you're not gonna have any mistakes. Because accidentally, if you do it, this simplification in non-consistent way, you can lose some solution or you can get something which is not equivalent to your original system. Yeah. Okay, let's consider another example, which is a little bit slightly more complicated because it has infinitely many solutions. Yeah. Okay, it's very similar system of linear equations. Again, we proceed absolutely like on the previous slide. You simplify it, you subtract the first equation from the second and then from the third, multiplying, of course, by appropriate number, 3 and 4, yeah, and you get something like this. And already at this point, you see that these two equations are the same. So basically, one of them is redundant. We don't get rid of it immediately. We can actually keep simplifying, and you get this system of equation, which is clearly simpler than the original one. But again, each of the steps is just simplification of your system of linear equations. And here I keep deliberately this equation 0 equal to 0 to basically remind you that this is equation. Yeah, it's a nice equation. Yeah, this is basically what's left of this equation. Yeah, and what we should do now. And now we see that we can take z to be anything. You can put z to be any number, and then you uniquely, once z is fixed, you uniquely determined x and y from the first two equations. So you solve the system of equation, but now your solution depends on parameter, which is z in this case. So when you vary this parameter, you have obtained infinitely many solutions. Yeah, this is very typical situation. Okay, to approach this solution of this system of linear equations consistently, let's first consider a little bit special case of our system of linear equations, where in the right-hand side of our equalities, we get only zeros. Yeah. So this is basically the same equation, system of equations as before, but all these b1, b2, bn numbers, all of them are zero. Okay. Such system of linear equations are called homogeneous. Yeah, but this is something we already know how to deal with. Yeah, this is nothing but the kernel of the corresponding matrix. Yeah, if you erase all of these xi's, and if you just keep a11, a12, a1n, am1, amn, and you put it into the grid, this is basically your matrix, which correspond to this system of equation. Then the kernel of this matrix, it's exactly this solution to this system of equation. This is in all examples which we already did before, when we found kernels of some matrices, we basically solved some systems like this. Yeah. Okay. And now we can apply some results about matrices to tell us something useful about solutions of the system of linear equations. And the most important, maybe probably better to say, the most applicable result is the rank nullity theorem. So applying the rank nullity theorem, we immediately see that if the number of your equations it's less than number of unknowns, then you always have infinitely many solutions. Yeah. So look, the rank nullity theorem tells you that the nullity of your matrix, the dimension of the kernel space, it's exactly n minus rank of the corresponding matrix. But the rank of this matrix cannot be larger than m, because this is going to be m times n matrix. Yeah. So if kernel has positive dimension, this basically means you have infinitely many solutions here. Yeah, of course, an important observation that unlike in not homogeneous case, unlike general case, this system of equation always has solution. Yeah, because if you substitute x1, x2, x up to the xn to be 0, then of course you get solution. Yeah. So here's the most interesting question is when you have finitely many solution and when you have infinitely many solution. Yeah. Again, rank nullity theorem, the most useful tool here. Okay. In homogeneous system of linear equations, so which we started with. So basically, if you have m times n matrix, you have some vector b, you have some vector u, and suppose you want to solve system ax equal b. This is a shortcut for our original system of linear equations. Yeah, basically we just rewrote it into the matrix form. So you want to solve this system of equation. We already know more or less how to at least deal with homogeneous system of equations. So if you put here b equal to 0, then this is going to be just the kernel of A. We know how to at least say when this kernel has positive dimension, when it has dimension 0, when it's basically it's only one solution, 0 vector. So when b is 0, we can say a lot of things about the system of equation. But in general, if b is not 0, what we asked in this lemma, we want to have just one solution of this. So we assume that this vector u, which I declared here, is a solution of this. How did we find this vector? It doesn't matter. So we just found it somehow. So we assume that this vector u is a solution of this system. Then this lemma says that all possible solutions to this system of equations can be represented in this form. It's u plus w, where w is a vector in the kernel. Okay, so again, u is fixed, u is unique, not unique, I mean, it's one solution of your inhomogeneous system of equation, of your general system of equation, which you found somehow. Yeah, and then you add to this u any element in the kernel, and you get solution of this. And vice versa, all such vectors give you all solutions of your system of equations. Yeah, so any solution of the system looks like this, where u is fixed. Yeah, how to prove this? You just take this equality and you just multiply it by a, and you have ax equal au plus aw, but aw is 0 because w lives in the kernel of a. So you have ax equal au, but au by definition is b, yeah, by assumption, it's a solution. So you get solution of this vector. Okay, so this is very handy lemma. The only question is basically how to find one solution, this initial solution of your inhomogeneous system of equations. Okay, but in many simple examples, you can just guess it. So for example, this is probably the simplest example I could cook up. So you have system of one equation, two unknowns, 2x minus 3y equals 7. Yeah, and you just guess some solution. So one solution, for example, is given by 5, 1, vector 5, 1. If x is 5, if y is 1, this is clearly equality. So this vector gives you the one solution of this. And then once you found this, you erase this 7, you put here 0, and you have the system 2x minus 3y equals 0. And you need just to find kernel of this 1 times 2 matrix, and this kernel, for it's one-dimensional, its basis is vector 3, 2. So all elements in the kernel looks like this, vector 3, 2 multiplied by t, and t is any real number. So by this lemma, this is our solution of the system. Of course, this is clearly be solved, the system clearly be solved without any tools. Of course, you get the same answer. Okay, good. So as I already mentioned, for homogeneous system of equations, we have basically two possibilities. Either we have one solution, which consists of vector 0, 0, 0, 0 vector, or we have infinitely many solutions, because for homogeneous system of linear equations, solutions are just the kernel of the matrix. The kernel is a vector subspace, so vector subspace either consists of one vector, which is 0 vector, or it contains infinitely many vectors. When we work with real numbers in this lecture, we assume, of course, everything is real. Yeah, so we have infinitely many real numbers. Yeah, okay. But when we deal with non-homogeneous system of equations, this is no longer the case. Yeah, so what could happen? It could happen that for example, the first equation looks like absolutely like the second equation, but maybe multiply by 2, all this a21, a22, a2n, it's the same as a11, a12, a1n, but multiplied by 2. But maybe b2 is not obtained from b1 by multiplied by 2. Maybe, for example, they different. Maybe b1 is 1 and b2 is 4. And in this case, of course, this when you subtract one equation from another, you get 0 equal to 3. And then such equation doesn't have any solution. So we have another possibility, which we didn't yet meet in any examples in this lecture, but this is a possibility. It may happen that we don't have any solutions. To be precise, this is very simple special case of this. You can assume that, for example, all left-hand side is 0. Yeah, you take corresponding matrix to be 0 matrix. But if on the right-hand side, not all, at least one number is not 0, then of course you get a contradiction. That basically means you have no solutions. Okay, how to deal with these cases? So basically, using the lemma on the previous slide, you see that we have three options. One option is you have no solutions at all. It means in the lemma on the previous slide, we could not find vector u. Vector u was your initial some solution of this system of linear equations, which you found somehow. There is a possibility that this is impossible. You cannot find the solution. So this lemma on the previous slide is not applicable. Okay, so there is one option. The second option may be that you have exactly one solution. So basically means you guessed one solution, or maybe you found it using some tools, and there's no others. Yeah. And the third possibility, you have infinitely many solutions. Yeah. How this follows from the previous lemma, then again, if we have no solution, it's no solutions. Lemma is not applicable, but we just have no solutions. If we have one solution, we can apply the previous lemma. We know that all solutions can be obtained, but as a sum of your solution you just found and any element in the kernel. So if kernel is a 0 vector, then you have this case, you have exactly one solution. If the kernel is a positive dimensional vector subspace of Rn, then in this case you have infinitely many solutions because you have infinitely many sums. Yeah, okay. Basically, this immediately gives you, if you apply result from basically the previous parts, if you apply rank nullity theorem, you immediately get that your system of equation has exactly one solution, if and only if rank of your matrix is n. Yeah, this is basically follows from rank nullity theorem, because when rank of the matrix is n, if and only if its nullity is 0. Yeah, by the rank nullity theorem. But nullity is 0 means that dimension of your kernel of your matrix is 0, what does it mean? It means that your kernel consists of only 0 vector. It means if you erase all of these bi's and you put here zeros, then the corresponding homogeneous system of linear equations has only unique solution given by 0 vector. Okay, and then by the previous lemma you have unique solution of this inhomogeneous linear system. Okay, this is very handy. Now, since we kind of want to translate everything in the matrix form, and originally we used a matrix equation like AX equals B, where B was a vector, X is a vector consisting of unknowns, and A was our matrix. But it's more handy if you don't have variables at all. If you remove all of your unknowns and you keep everything as a one matrix. So you want to encode your original system of equation as a one matrix. Okay, what this matrix should be? Of course, it should be your matrix A, which we used on the previous slide. But then you take this numbers B1, B2, Bm, numbers on the right-hand side of your system of equation, and you put it as an extra additional column. But in order to remind you that this is actually not part of the matrix A, this is terms in the right-hand side of your equation, you put here this vertical bar. Yeah, so this is basically a matrix which encodes the whole your system of equations, but the key player here is this matrix A, of course. Yeah, so you put this vertical bar to split them. Yeah, and usually this is called augmented matrix of your system of linear equations, Ax equal B. Okay. Of course, its size is m times n plus 1, because we added one column here. Okay, again, this is just a shortcut matrix, probably matrix translation of this system of equations. Yeah, and we have this nice lemma. Then your system of equation has solution if and only if rank of the matrix A equals to the rank of the augmented matrix A, which is denoted by A hat. Yeah, if ranks of the matrix and its augmented matrix are the same, then solution exists, and this is if and only if. And this is quite straightforward to prove. Again, this is nothing fancy. This is basically just a nice way of answering the question when you have a solution of system of linear equations. So how to prove this? Again, if Ax equal B has a solution, it means if you can find such vector x such that Ax equals B. What does it mean? Again, very important observation, which I used already multiple times. So when you multiply A, matrix A by vector x, this is a linear combination of columns of A. So basically means, by definition, this guy, Ax, is contained in the column space. So if it's equal to B, and if you look at this matrix, and you just remind yourself what is rank, rank is a dimension of the column space. But the column space of A is a span of these n columns. And then if we know that solution exists, it means that B, this vector B, which basically this n plus 1th column, it's a linear combination of these columns of matrix A, the first n columns. So it's contained in the same span. So of course its dimension of the column space of the augmented matrix is the same as dimension of the column space of A in this case, because in this case, if solution exists, this vector is just a linear combination of the first n vectors. Okay, yeah, and vice versa. What's possibility that the rank of augmented matrix is the same as rank A? You take a column space of the matrix A, and then you get another vector. You add another vector to this n plus 1th column of the augmented matrix. If rank doesn't increase, it basically means that this vector is contained in the column space of A. Yeah, and then in this case, of course, as I already mentioned by this important observation, there exists a vector x such that AX equal B. Again, this equality is equivalent to say that B is a linear combination of columns of A with coefficients given by the entries of the vector x. Okay, this is a nice answer to the question when solutions exist. Yeah, but in applications, of course, you very rarely use this lemma explicitly. If you want to find the solution, it only tells you that it exists, but how to find it, it doesn't tell you. Okay, in particular, if you apply this lemma and the lemma on the previous slide, we see that system AX equal B has a unique solution if and only if rank of the augmented matrix is the same as rank of matrix A equals to n, if all of these numbers are the same. Okay, good. Now, we more or less answered all theoretical questions about how to determine do we have infinitely many solutions, finitely many solutions, unique, in terms of some theoretical material, in terms of rank. Now let's go to a more practical topic, how to basically find, how to solve this system of equations, how to explicitly in examples find solutions. And we already implicitly use this topic when we simplify two 3x3 systems of linear equations in the very beginning of this lecture. So we used some tricks how to simplify our equations. We use some steps, some recipes how to simplify our equations. But we probably did it in this example not in a very consistent way, because this was just examples. Okay, now let me formalize what we did. So we interchanged two equations. We swapped two equations. We found that one equation looks better than another, and we put it, for example, from the second place to the first place here. It was our choice. Then we multiply some equation by non-zero scalar, non-zero number. Yeah, of course, on both sides. Yeah. And then we took one equation, another, and we add to one equation, another equation. Yeah, basically, this is only operations we did in these two examples in the beginning of this part of the lecture. Okay, and this, we can say this is elementary operations with equations. But since we decided to use a matrix language to work with systems of linear equations, we have to translate these operations into the operations with matrices, with augmented matrix. And what we're doing here, we're doing some operations with rows of the augmented matrix. Yeah. So basically, let us fix some m times n matrix, which correspond to some system of equation. Yeah, you have some B is a vector in Rm, A is augmented matrix of the system of equation Ax equal B. Yeah. And these three operations with equations can be translated into language of matrices as follows. So we interchange two rows. Second, we multiply a row by non-zero scalar. And third, we add a scalar multiple of one row to another row. Okay, just an advice. Don't forget when you do operations with rows, when you apply what is called elementary row operations to augmented matrix, don't forget that what you're doing is just simplifying system of equation. So sometimes it just maybe easier, it's not even to rewrite your system of equation into matrix form. Sometimes it's actually convenient to rewrite your system of equations into matrix form and then apply elementary row operations to simplify your matrix. But when you do this, remember that what you're doing is basically implicitly you simplify your original system of linear equations, which in the matrix form is written here. Yeah. So to keep track of your operations, this is actually quite useful. Also in solutions, if you want to solve some problem, you have to explain which operations you performed. In my two examples, basically just explicitly said, I did this, but it takes some space. In order to make it simpler, we use special notations for these row operations. If we interchange two rows, I rows and j rows, we write something like this. Ri interchange with rj. It means we swap two rows, ith row and jth row of your matrix. If you multiply your matrix, your row, some given row, Ri, row number I, by scalar lambda, we write like this. So you replace row Ri by the row lambda Ri. Lambda has to be non-zero, of course, otherwise you accidentally get more solutions. You don't get equivalent system of equations. Every time you perform elementary row operations, it should be invertible. So you should be able to return back to your original matrix or original system of equations here. And the final operation, if you take row number jth row, you multiply it by some lambda and add to the ith row. Yeah, and this is written like this. Ith row, which we denote by Ri, yeah, is replaced by Ri plus lambda Rj. Okay, this is very algorithmic. This is very transparent. Yeah, so this are called elementary row operations. Performing them, you can actually obtain solutions to many simple, not very big, not very complicated systems of linear equations, basically by hand. Of course, if your system of linear equations is huge, you have to use help of computer. But keep in mind that when you use the help of computer, it means that someone programmed this package for you, which solves system of linear equations. And behind this program which you're using, you have this elementary row operations because they algorithmic. Okay, here's an example. We have this augmented matrix. Again, it's nothing but the system of linear equations with three unknowns. Your vector B is just 3, 4, 1. This is your matrix A. Yeah, so this is just the system of linear equations that is given in the matrix form. Yeah. Okay, and we want to simplify it using elementary row operations. Basically, this is, of course, the same example which I already used in the beginning of this lecture. Yeah, it's just written in the matrix form. Yeah, and let me just translate what I did earlier into my new language of elementary row operations. Yeah, yeah. This is basically the same what I already did earlier, a little bit more. And why more? Because basically now this my notations are very space consuming. So I can actually put in one slide much more than I could put in one slide when I use notations for system of linear equations. Yeah. So again, yeah. So if you remember this example, we swap first and the second row. Then here we actually performed two elementary row operations at once. My suggestion: don't perform more than two elementary row operations simultaneously. Otherwise, it's easy to make a mistake. Yeah, okay, hopefully I didn't get any mistake here. Yeah, and this is basically a system of equations. This augmented matrix corresponds to the system of linear equations we solved in the beginning of this lecture. Yeah, but now we can proceed more. We can, even if we wish, we can simplify it more. We get this, and then we get this. Yeah, yeah, of course. If we have this system of linear equations, then we can still solve it easily. Yeah. So, for example, what the last equation means? It means minus 23z equals minus 46. Yeah. So you conclude that z is 2. Yeah. But we can actually proceed simplifying a little bit, and you get this. And this is, of course, simpler than this. Yeah, a little bit, but simpler. Yeah. So you have z equal 2, y equal 1, and x equal 1. Yeah. Of course, you can extract the same solution from here, but it's easier, of course, here. Yeah. Okay. This is typical example how you solve system of linear equations using elementary row operations. Okay, now philosophical question, theoretical question. What these elementary row operations preserve? Of course, they are designed in such a way that they preserve the space of solutions. Yeah, not like set of solutions. Your solutions should be the same, because otherwise it's just useless to use them. Yeah, the goal of using elementary row operations is basically to transform your original system of linear equations into a much simpler one, such that you can easily solve. But of course, your goal is to solve original system. So the set of solutions should be the same. Let me formalize this. So you have two matrices A prime, and you have two vectors B prime. You have two augmented matrices, which correspond to this system of equation and to this system of equation, AX equal B, A prime X equal B prime. Yeah. And we now assume that one system of equation can be obtained from another using elementary row operations. In matrix language, we say that if this augmented matrix A hat prime obtained from A hat using elementary row operations, yeah, we assume this, then they have the same solution. AX equal B, if and only if A prime X equal B prime. Yeah, you don't change set of solutions. You don't get new solutions, you don't lose any solutions here if you use elementary row operations. In particular, if you apply the same only to the A part of the matrix A. Remember, augmented matrix consists of matrix A plus one extra column consisting of vector B separated by the vertical line. Yeah, but if you obtain augmented matrix one from another using elementary row operations, then of course matrices A and A prime going to be related by the same elementary row operations. So in particular, elementary row operations definitely preserve row space. Yeah, why they preserve row space? Because what you're doing, you basically just changing vectors in the row space. Yeah, if you have one row, it's an element of the row space. If you multiply it by some number, of course, this is an element of the row space, because row space is a vector subspace. Yeah, so elementary row operations preserve the row space. In particular, it preserves the rank, because we already know that rank is dimension of the row space or dimension of the column space. It's the same thing. Yeah, and it also preserves the kernel of the matrix A. Why? Because the kernel of the matrix A is just a solution of homogeneous equation AX equals 0. So basically means if I take this lemma, I put here B equals 0 and B prime equals 0, I get that the translation of this lemma going to be that the two kernels are the same. Yeah. So this line is a special case of this lemma when B and B prime equal to 0. Okay. Important remark that the column space usually not preserved when you do elementary row operations. So keep this in mind. When you play with rows, you preserve rows, but you don't preserve column space. Yeah, column space can be different. Okay. Now it's very common, very popular topic for any linear algebra book. In my opinion, it's a little bit too popular than it should be. It's called row echelon form. So basically, what is the row echelon form? Okay, here's a definition, and I'll give you example in a second. But basically, this is one of the simplest, but not the simplest, one of the simplest shapes you can put your augmented matrix into, or any matrix into. Okay, let me, while you're reading this definition, let me give you an example, and let's now read this definition again. So we say that the matrix A is in the row echelon form if any row consisting of entirely zeros are at the bottom. So basically, like in the very first examples, which we considered 3 by 3, when we have infinitely many solutions, if you remember, I put my redundant equation 0 equal to 0, I put it in the last line. Yeah. So this corresponds to the fact that this 0 equation, 0 equal to 0, we like usually put in the bottom of my matrix if it's in the row echelon form. Yeah. So first condition that all 0 rows in the bottom of the matrix. It's okay. We can do this by swapping the rows always. Yeah. And the second condition that if you take your non-zero rows, the first non-zero entry of your row, you call it leading entry. Yeah. And the second condition that if you have this in every row, if you take the leading entry, that basically all numbers to the left is 0 by definition. Yeah. But another thing that if all numbers below it must be actually 0 as well. If you take a leading entry of every row, and if you take all the corresponding column, and all entries below this column, all entries in this column below this leading entry must be 0. So your matrix should be in this shape. Yeah, you see? The first, basically the leading entry of every row is to the left of all leading entries below it. So it should be like this shape. This is why it's called row echelon form. It looks like an echelon. Yeah. So, okay. Good. Now, usually in practice, when you solve your system of equations, you underline leading entries. Yeah, they play important role. Yeah, they play important role because, for example, of this lemma. If you have a matrix in the row echelon form, then the transposes of its non-zero rows form a basis of the row space. Okay, look. What is a row space? Row space is a space generated by linear combinations of your rows. It's basically span of your rows, of your matrix. So all possible linear combinations of these rows. Yeah, but of course, in this case, if you have a 0 row, it's just a 0 vector. You don't even need to consider it when you take a span. Yeah, so span of rows of this, for example, matrix is the same as span of the first 3 non-zero rows. But in this case, when matrix is in the row echelon form, you also know that these rows are linearly independent. So if you have spanning set, and which consists of linear independent vectors, these vectors form a basis of your vector space. And so basically, to prove this lemma, it's enough to show that the rows of a matrix in the row echelon form are linear independent. But if you just check definition of linear independence, you see this immediately. For example, in this case, if you want to show that these 3 rows are linear independent, you say, okay, let's consider the linear combination with some coefficient lambda 1 multiplied by the first row times plus lambda 2 multiplies the second row plus lambda 3 times the third row. If this combination is 0, then you compare the entries of your vector in the first, which correspond to the first entry. The first entry is going to be lambda 1 times 1, all other zeros equal to 0. So you get lambda 1 equal 0. Similarly, what's going to be second entry? Second entry going to be 2 times lambda 1 plus 6 lambda 2, but you already know that lambda 1 is 0. So what you get is 6 times lambda 2 equals to 0, which is implies that lambda 2 is 0. And then you continue and you get all these lambdas going to be 0, and this means exactly linear independence. Again, check this lemma in this example, and you get basically the idea of the proof of this lemma in general. Yeah, this is why row echelon form is important. For example, if someone asks you to find the basis of the row space, the only thing you have to do, you have to apply elementary operations to transform your matrix into the row echelon form, and then you take non-zero rows, and this is your basis. Okay, and of course, if you know the basis, you know the dimension of the row space. It's just a number of elements in the basis, and this gives you the rank of the matrix. Okay, good. But as we already saw from the examples 2 slides ago, that row echelon form is a simple shape of a matrix, and which correspond to the simple shape of your system of linear equations, but you can simplify that more. So for example, if you look at this matrix, you can apply an elementary row operations, you can simplify it more. Yeah, you can, for example, divide this second row by 6. Of course, you get some ugly rational numbers here, but the leading entry going to be 1. And this row, the third row, you can divide by 10. So here you're going to be 11 over 10, but here you're going to have 1. Okay, this is a little bit simpler. What else can you do? Then you can subtract from once you divide, as I said, you can subtract second row from the first row multiplied by 2. And then you remove this number 2, this number, instead of number 2, you're going to get 0. Of course, it changes all these 3 entries, and it's going to be some complicated looking numbers, but then on top of every leading entry, you're going to get 0. So if you continue, you can do this with every leading entry, and this gives you what is called reduced row echelon form. So basically, by definition, matrix A is said to be in reduced row echelon form, usually abbreviated like this, RREF. You can see this abbreviation quite often in many sources, yeah. And so your matrix in reduced row echelon form, if it's in the row echelon form, and in addition, if all leading entries are 1, and each column containing a leading entry 1 has zeros everywhere else. So by definition of the row echelon form, in the corresponding columns, you have zeros below the leading entry, but if it's in reduced form, zeros also is on top of the leading entry. So this is very simple looking matrix here. And then we have the theorem, which I implicitly mentioned already on the previous slide, that every matrix can be put in the reduced row echelon form using elementary row operations. In particular, it can be put in the row echelon form. Of course, the row echelon form is it's a more general form of the, not more general form, it's a weaker form that of the reduced row echelon form. Yeah. Okay, so what this theorem tells you? Basically, this theorem tells you what we already saw in examples, that every system of linear equations can be ultimately simplified, such that it's as simple as possible. The simplest shape of a system of linear equations, it's if this corresponding matrix in the reduced row echelon form. Okay, and then we can restate corollary of what I already said on the previous slide. The rank of a matrix is the number of non-zero rows in its row echelon form. This follows from the lemma on the previous slide. Yeah. Okay, and a special case when we consider square matrix. And if you know that your matrix A is invertible, then your reduced row echelon form must be, of this matrix must be identity. And basically, this follows from definition of reduced row echelon form. So look, if your matrix is invertible, its kernel is trivial. Its kernel consists of 0 vector. It means, and it's square, yeah, by assumption here. So if we reduce your matrix into the row, if you put your matrix using elementary row operations into reduced row echelon form, we preserve the kernel, and then you get a square matrix whose in the reduced row echelon form, and whose kernel is 0. So, and in particular, it means that there is no 0 rows. Yeah, because if you have a 0 row, that your rank drops. So in this case, it's impossible. So then you immediately obtain that just basically by definition, if you have no 0 rows, on the diagonal you must have ones. All diagonal entries are leading entries, and below them and above them, all other entries are 0. This is exactly means identity matrix. Okay, this is a special case for square matrices. Okay, let's find some applications of the reduced row echelon form, which I already mentioned a few slides ago. We can use it to find the row space, to find the basis of the row space. We can use it to find the dimension of the row space, which is the rank of the matrix. We also can use it to find the kernel of the matrix, because this is basically the whole ultimate goal of this elementary row operations, to simplify your system of linear equations such that it's easy to solve. Kernel of a matrix is given by homogeneous system of linear equations. Yeah, so let's do it. In this case, you have this matrix, and you want to find its kernel. Its kernel is a system of linear equations, which is given by equation Ax equals 0, where x is it's a vector x1, x2, x3, x4, x5. Yeah, in R5. Okay, you just apply reduced row echelon form. I didn't have enough space to do this on the slide because it's in this case it's a bit bulky. Yeah, but you get this matrix. This is the reduced row echelon form of matrix A. But then you think, okay, so kernel of this matrix is the same as kernel of this matrix, but kernel of this matrix is easy to find if you multiply it by a vector x1, x2, x3, x4, x5, that the last row, the last column, the last row, it's give you equation 0 equal to 0. The fourth row give you equation x4 plus 4x5 equal to 0. Yeah, and then similarly, you can translate this into system of equations, and you can solve it, and you get solution. Okay, so basically, you can take x3 and x5 to be any possible, any number. This is your parameters. Usually, in most of books on linear algebra, they are called free variables, and you can express all other unknowns in terms of them. So put it this way: if you multiply this matrix by vector x1, x2, x3, x4, x5, and make it equal to 0. And then if you say, okay, I know x3 is S, I just give it a different name, and then x5 is T, then you can express x1, x2, and x4 in terms of S and T. Again, why? Because of this non-zero leading entry. So basically, you declare these variables which correspond to the columns different from that doesn't contain leading entries. This columns becomes free variable. Like in this case, it's going to be column number 3. You see there's no leading leading entry here. Your leading entry, this guy, and this guy. So third column is doesn't contain any leading entry, and the last column, fifth column, also doesn't contain. So it means in this situation, you can express the correspondent unknowns which correspond to leading entries x1, x2, and x4 in terms of x3 and x5. So usually you can denote this variables x3 and x5 by different letters. I mean, just so it maybe looks better. And you express your x1, x2, x3, x4, x5 in terms of s and t. And then you can either leave it as it is, or you can split it as a s times some vector plus t times some vector. And you have this. And when you express it, you see what this expression is. But this exactly means that the kernel of A is a span of these two vectors. So these two vectors is the basis of your kernel, basically by definition. It's easy to see that they are linearly independent, of course, but this also follows from your solution. Yeah, we know from rank nullity theorem, for example, that the kernel is two-dimensional. Yes, because rank of this matrix is a number of non-zero rows, which is 3. So you apply rank nullity, you get kernel is 2. Okay, by the way, there's another way of proving rank nullity theorem using elementary row operations and reduction to the reduced row echelon form, which has some benefits. Okay, good. Let's consider one more application of reduced row echelon form, which is a bit unusual, but it's actually kind of funny. How to find inverse of a matrix. We already discussed in this lecture how to find the inverse of any square matrix, and in particular, using this formulas we discussed, you can find quite easily inverse of a 3 by 3 matrix. Of course, if it exists, if determinant is not zero. Yeah. So if I give you this matrix, okay, you can say I apply this formula, I find the inverse of this matrix. And this is not hard, but there's another way, surprisingly, which uses reduced row echelon form. Okay, let me just basically show you how to do this, and you will see. So first, you consider this strange looking matrix. You put your original matrix here, and you put on the right hand side, you put identity matrix. And you separate them by vertical bar, so you don't forget that your original matrix is this one. And then what you do, you start performing elementary row operations to this matrix, trying to put your matrix A into the reduced row echelon form. But we know that you have two options. Either you succeed, and okay, you succeed always, but I mean, either your matrix has non-zero determinant, and then you get identity matrix as a reduced row echelon form, or maybe you get some matrix with 0 row, and in this case it basically means that it has non-trivial kernel, and in this case determinant is 0, and in this case inverse does not exist. Yeah, so there's two options, but in this case, everything is going to be fine. So let's just perform elementary row operations to put this into reduced row echelon form, which is going to be identity matrix. Okay, we just do this. This is not hard because this matrix is not very complicated. So, okay, you for a while, for a second, you can ignore the right-hand side of this matrix. You can ignore this 3 by 3 matrix in the right part of this 3 by 6 matrix here. So you only care about the left part, the 3 by 3 matrix in the left. This is your original, you simplify, you get this, yeah. And then, very nice observation that what you get on the right-hand side, this is exactly inverse of your matrix, yeah. Okay, I'm not sure this is much faster algorithm when you have a 3 by 3 matrix than applying the formula which we discussed today. But when matrix is huge, then this is much faster. Yeah, so this is actually quite useful. Yeah, and so even for 3 by 3, maybe this is faster than using the formula. Okay, This is probably everything I wanted to say in this part of this course. Okay, my usual impression that students have no problems with applying elementary row operations to matrices. You all very good at this, so I'm absolutely confident you will learn quite easily how to apply them and how to reduce matrix to the reduced row echelon form using elementary row operations. Okay, let me stop the recording here.